Okay, so this is your week 5 tutorial session. Uh, so today we'll look a little bit into these topics, Van der Waals equation of states, and we'll see some related problems and also try to understand little about Pauli's paramagnetism and so on. We'll also see some related problems to it as well. So yeah, so again, these are some related topics that could, I mean, for your week 5 of your course, and also this can also you can find some relevant problems in your assignments also, so you can relate that. So yeah, so we know Van der Waals equation of state for a real gas is something is given like this. So uh, uh, Alok, like, are you are you having any doubt?
Yeah, I have a doubt, but it's regarding something else that
Uh-huh.
it has been emailed that the uh, lecture of week 6 has been uploaded,
Uh-huh.
but I am not getting that in my account. I am not getting that, neither the lecture nor the tutor nor the assignment.
Okay, okay. Let me check quickly.
Hmm.
Uh, so here I can also see up to week 5 there are topics. There are like when the assignments and everything are there up to week 5. So week 6 is not yet. I mean, they have not posted it out, or so you have got the email about
Yeah,
week
yes,
six.
pro- yeah. Probably yesterday I got the email that the assignment has also been uploaded and the timeline has also been given.
Okay.
Timeline has also given there, but I am not getting anything in my account.
Probably like it could be some error, probably from their end. So I will try to email them, or you can also try like
I
like,
I emailed them, but I haven't got any reply.
okay, okay. Let me. I will also try from my end. I will tell them that okay, that week 6 is not yet posted, but it has been informed that week 6 is already running live. Right.
Okay, thank you.
Okay. So, or do you have any other issue?
No, nothing right now.
Okay. Uh, yeah, fine. So yeah, we were talking about Van der Waals equation of state. So like I mean, this is not the equation of state that you see for an ideal case or for a perfect case. So it is for uh, uh, like for some real or imperfect case, you can have this kind of equation of state. So here you see specifically two constants, or basically there are two corrections that has been made to the usual perfect case equation of state. So we know the perfect case equation of state is something given as PV equals to nRT. So in volume and pressure, we make a correction like such that it will actually mimic the a sort of real gas. So first we like um, we make a correction on the pressure term. So if you take a pressure in certain volume, or else like first we start with making the start with the correction of volume. So far in perfect cases you have seen that like the particles in that gas were treated as some point particles. So here we consider actual like some finite size of the particles, and that is corrected using this constant minus b. And then similarly, so if your volume is some certain volume of container you are taking, and within that container you have all the gases, then you cannot have the exact volume of the container and the exact volume of the gas. It would be some less than that. So uh, uh, yeah, it has to be something less than that. Uh, then then again for a then again for pressure also there is something you will find. I mean, pressure, like for example, uh, within deep inside the container, uh, I mean, there are gases all around. So, if you consider some gas particle within the small region, you will, so, uh, so there are gas particles all around. So, uh, so within volume of the container, if you see a particle and its corresponding pressure that it is under, you will see that that particle has pressure from all around, like from all directions, and you will see that like it is some it is a type of uniform pressure that you will find wherever you locate any particle within the volume. So you will see the same thing, but across the surfaces you will see that like the pressure outside, I mean this side, it has no pressure. Uh, so on if a particle is right on the edge, so you will see there will be pressure from this and this end, with only from the side of the container where gas is filled, not from the outside. So this is one correction where you have this quantity A. So this A is something proportional to one like something this A is proportional to V to the power minus 2, and likewise as I said, like even the volume, so the entire volume cannot be the volume of your gas, because the this gas particle is not exactly point, so it is something like it has some finite size. So that takes into account of this. So this is how like you can have this van der Waals type. Yeah, this is some type of real gas equation of state which you can like get it through van der Waals equation of state. If you see exactly like the how equation of state really like changes over various thermodynamic variables. So we have seen isotherms and isobars, all these curves for ideal gases. So for van der Waals gas also you can uh, get the same thing from this uh, equation of state as well. So you'll find that let's say you start with some temperature and you fix the temperature and you vary pressure and volume. So you get something like this kind of curves. So or if you drop the temperature, you will get this curve. So likewise, you will go on. So but you will find a temperature there. You will see that at certain point, uh, it will have this kind of nature, meaning. Uh, so. uh, um, uh, yeah. So at certain temperature, you will find what happens that I mean this is basically some threshold value. What happens beyond this threshold value, if you lower the temperature further, if you go on to other temperature, um, down this, so you'll find uh, wait a minute. Yeah. So beyond this temperature, if you go, so uh, so you'll find that you will get some kind of a minima here, and then so initially your P decreases upon increasing volume, and then it will start to increase as well, and similarly it will also go to some maximum value, and then again it will decrease. So you see that like across this temperature, what happens, the uh, you're basically the your I mean your gas is basically liquefying at this point. So and then again you will get a gaseous state here. So it is like you get a like uh, phase transition in this at this temperature, beyond this temperature. So like you so yeah, so you can say that like at this temperature, so different phases coexist. Basically, the gas that you started out with, like that, can undergo liquefaction. So and so it undergoes phase transition. So and and this point you can say it is your like critical point. So it is like neither maxima nor minima. So this is where your I mean your uh, transition temperature, you can locate it. So this is the exact temperature where you get a where you get the critical point. So so this is like for example, you have certain gas that obeys this van der Waals equation. So and you are reaching some temperature Tc, then you are already reached the phase transition temperature. So if you go further down, then you will find different phases, like your state of the uh, your the gas which is trapped inside the volume can also change. So yeah, so we can see more about it going through this problem following here. So yeah, so using a van der Waals equation of state, express the van der Waals constants in terms of critical variables Tc, Vc, and Pc. So, that means at critical temperature, you have to calculate what will be your critical pressure and critical volume and critical, yeah, corresponding to that critical temperature, and using the van der Waals equation of state. So, yeah, okay. So you have um, you have the van der Waals equation of state, which is in the following way. So I can further write this as and minus A over B square. So to get the critical point, to reach the critical point, as I was talking about, so that is the point where you find a inflection point. So this is kind of a like a inflection point. So where you do not have any maxima or minima. So that is the inflection point, which is otherwise known as. So at inflection point, like at inflection point or uh, um, at t equals to tc, you will have rate of change of pressure with respect to volume uh, at t equals to tc will be uh, 0, and also uh, so this is not just t equal to tc, but also at like v at point vc also. So at tc and pc you have 0. So it is like at inflection point which you know that uh, the rate of change of slope of the curve, and also its change in tangent also, both remains 0. So it's like like neither maxima nor minima. So uh, yeah. So if you take it's just straightforward, you can take the derivative with respect to volume first, and and you fix the temperature at constant temperature. You take the derivative of pressure with respect to volume, so that will be uh, nRT over V minus B square minus or plus 2A over V square. So similarly, you can take this will be plus 2A over V cube. Similarly, if you take the derivative again, so you have 1 over V minus V cube, and then 6A over V4. Yeah, then at critical temperature, or at the critical point, you have del P over del V. T at constant temperature is 0, and then also del square P over del V square is also 0. Then if you put both equations to 0, and then if you solve it, so this will be at V equal to Vc, and this will be also V equal to Vc, and P equal to Tc, and this is also P equal to Tc. So yeah, then like in doing that, you will find that your uh, volume will be Vc will be 3b, and your temperature would be related something as following: 8A over 27b. Then from there you can put it in the equation of state, and then you can find your critical pressure will also go like something A over 27 B square. So yeah, so or otherwise this constants, your van der Waals constants are okay. Yeah. So or the van der Waals constant, which are basically your correction factors A and B. In terms of critical variables, you can write it as A would be um, so here A would be like if you like just take the ratios and you'll find out this will be something 3 times VC square, and your B is simple. It is VC over 2. So yeah. So yeah. So this will be, so these are your critical variables for the van der Waals equation of state, and your constant can further be related like this. So yeah, then second, you have to find out the dimensionless ratio PV over RT at the critical point. So at the critical point, we just found out what are the critical variables like critical pressure, volume, temperature. Then what would be the ratio of this thing? So we already have it. So so at critical point, uh, so your dimensionless ratio uh, PC or times VC over RTC. So, so PC we just found out, which is A over 27 B square, and your VC is 3B, and R you have, and so so RTC is basically 8A over 27B, or 8A over 27 times B. Yeah. So if you take N to be 1 for now, let's say you consider for like 1 mole of gas that you are considering, then this is just a very simple ratio, which is 3 over 8. Right. Then you have to like find out the what are the yeah, from these new variables you have to like find out what are the reduced van der Waals equation of state. So your reduced pressure, reduced volume, and reduced temperature, they are defined in this way, which is basically scaled by these critical values of the uh, van der Waals constants, or basically the critical variables, which are critical pressure, volume, and critical temperature. So using this reduced uh, variables, you have to find out the new uh, you have to find out the new equation of state. Yeah, yeah, yeah. So you know the so we which we started with. So the van der Waals equation of state, which is this. So if I substitute this in terms of critical variables, and then uh, uh, so so critical variables, your PR is given as P over PC, VR is given as V over VC, and TR is given as T over TC. So that means your pressure is something PRPC, and this is VRVC, and then you have TRTC. So from here you can write it down. You put it in the van der Waals equation of state, and then you see uh, TRPC plus A over um, VR square VC square, then uh, VRVC minus B equals to R times TRTC. So or it would be or it would be better if I could start from here. So we also had P equals to nRT by V minus B square, right? So it is V minus B, then minus A over V square. So this is A over V square. Let me see. Yeah. So from here as well, what you can do, you can uh, substitute this uh, reduced variable PRPC equals to uh, NRTRTC over V minus over VRBC minus B minus A over VRBC square. So now you can put uh, uh, PC, which we calculated here. So PC, as we calculated just before, which was A over 27 B square, and then we also likewise calculated TC, which was uh, rather we calculated RTC, so which is 8A over 27B. So NRTC 8A over 27B, and likewise we also have VC, which is uh, 3B. So you can use them here, and then we'll find out the relation, which is PR equals to 8 times TR over 3VR minus 1 minus 3VR square. So yeah, so this will give you the reduced uh, van der Waals equation of state. Uh, right. Just give me a second. Like I'll be here. Uh, yeah, yeah. Like I was. Yeah. So then next, what we had. So for the van der Waals gas, yeah, the reduced pressure. The reduced pressure is given to be 1 and the reduced temperature is 1, then what would be your reduced volume? So yeah, it's just straightforward from here. So uh, so if let's we can do this like we just have to uh, give the values and we have to just find out what would be your reduced volume. So yeah, so your uh, reduced pressure is given to be 1 and also reduced temperature is also given to be 1. So, so using this like we have if you put these values in your reduced equation of state. So from reduced van der Waals equation of state, so you have 1 equals to 8 times 1 3 vr minus 1 minus 3 over vr square. Then yeah, so so here you can multiply uh, on both sides. So here I'm trying to eliminate the denominators. So basically you can uh, you have to just take out the yeah, I'm multiplying the LHS and RHS by this factor. So such that I have 8 VR square minus 3 times 3 vr minus 1. So so if you people have any doubt or anything to ask, any question, you can speak. You can unmute yourself and can speak. So okay, then or this I can also write it as 3 times. So here I have vr cube. So, so yeah, I'm getting some kind of a algebraic or a, cubic polynomial here. So then I have minus vr square. So and minus 8 vr square. Then I have 9 vr minus 3. That will be 0. So and so if you see that like it is something coming. If I take, so this is minus vr square minus 8 vr square, that will be minus 9 vr square. So I can take overall factor of 3 outside. So that will give me vr cube minus 3 vr square plus 3 vr minus 1 equals to 0. And so this is basically so 3 times vr minus 1 cube equals to 0. So uh, so this forms a cubic of basically a cubic expression. So this is vr minus 1 to the power 3. So here obviously our factor is 3. So the only way that this can be 0 if your vr is 1. So basically vr minus 1 cube uh, uh, is 0. So that means your cube root of 1. So or basically vr is 1. So, yeah, not cube root. So but for vr equals to 1, you have uh, vr equals to 1, tr equals to 1. So this also implies your vr is also 1. Yeah. So do you have any problem here? Anything not understood? Uh, Anything properly? Uh, I mean, these are something like I know the preliminary thing which you have also seen before, perhaps. So uh, if you have something to ask, you can ask. Okay. So next we can discuss something on Pauli paramagnetism. So so you have so far like you have uh, like uh, learned about uh, systems of statistical systems of various bosons or fermions. So here we'll see one type of fermionic system here where we'll consider the fermionic system uh, now in presence of some magnetic field. So this is some statistical system that we are considering here, like in some external field, which is here is your magnetic field. So yeah, so what is what happens here is like suppose if you have a some system of fermions which are non-interacting, of course, and spin half. So, like your spin half means your electrons and protons, all these are your fermions, and you put them in weak uniform field. And let's say you are at temperature, uh, let's say at temperature 0 Kelvin. So at 0 Kelvin, you have seen, like, because of Pauli exclusion principle, I mean, uh, no, like no two states can, or no two fermions can attain the same quantum state. So, uh, so basically, each quantum state can hold only one fermion per spin state. Like, because at least, even if you take some thousands of electrons, so one electron has, like, either has uh, spin up or spin down. So you can only place one spin up electron with only one spin down electron. Uh, so you cannot have any other electron, because that would be again spin up and spin down, which will violate the Pauli's exclusion principle. So yeah, so at 0 Kelvin, you will see that, like, fermions uh, fill up the uh, Fermi energy level. So this is something like some related problems also we have seen, like last week, or maybe a couple of weeks before. So yeah, so at 0 Kelvin, these fermions fill up energy level, as I was telling, because of uh, Pauli exclusion principle. Doesn't allow all fermions to fill the lowest energy level. So yeah, so because yeah, even at 0 Kelvin, which you have seen for some other, like, um, bosonic type particles, even if you take different energy levels, so bosons can, like, stay, all the bosons can be in your ground state, but fermions cannot, because of Pauli exclusion principle. Uh, if you are taking electrons, then it will be either two of them can fill the low state, and then likewise the two more fermions will start filling up the other successive uh, energy levels, and at one point they will reach a certain level where it would be completely filled, like in pairs. So that will be your the total. If you see, that will be your total Fermi energy. Means at 0 Kelvin, your fermions fill up to some energy level, some level, let's say level n. And so if you take the energy of each level to be something of equal energy, let's say epsilon. So your n epsilon is your Fermi energy. So even Fermi energy, we have also looked into its expressions. We have like calculated it. Uh, Also, some related problems we have seen. So it was something, if you recall it, it was like given to be something. Fermi energy was uh, x bar square over 2m on, and then 3 pi square n over v. So which is your number density, or small n, that was to the power 2 by 3. So, like, we have, like we have seen, we have calculated this, like, by using the density of states, and then uh, integrating out with all the energy. So uh, and you also require the probability function of the Fermi-Dirac, because fermions follow Fermi-Dirac distribution. So this is Fermi-Dirac probability distribution. From there, we know this. So yeah, so these are some informations that you already aware of. So now, what you have to do, like now the fermions now they are these are kept in an external field or magnetic field to be precise. So in that case, your uh, so if you also remember from your, I mean, from your like basic idea about classical electrodynamics uh, uh, course as well. So you can remember whenever you have some spinning particle, and if you spinning particle means like any like any charged particle or any charged object, any spinning charged object leads to some magnetic moment. So like a charged sphere or some charged disk or something. So if it rotates, if it spins, then it gives rise to some magnetic moment. So uh, so so we know uh, any spinning charged object or charged object or particle gives rise to magnetic moment, because they form a kind of a current loop. Because when you have, let's say, some conductor you have, and if you see the charges are flowing this way, then it forms a like a magnetic moment. Like suppose a wire is there and it is charges are flowing in certain direction, then it will that this loop will behave like a magnetic dipole moment, magnetic dipole. So it will yeah. So similarly, now instead of these objects, you have quantum particles like electrons, and we know for electron are quantum particles, and they have something some intrinsic property which is spin, and they are also charged particles. That means as they spin, like what we, I mean, we exactly really cannot see them spinning, but we can correlate with the ideas that we have that that spin and the charge of the electron can together give rise to a magnetic moment. So, so likewise, yeah. So, likewise, uh, fermions like electrons, protons can also give rise to magnetic moment due to their spin. And also remember the spin is something given as equal to half. So this spin they can be either up or down. So it has only two states. So uh, so likewise, your magnetic moment of these fermions will also be either plus or minus uh, 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 B. So mu B is some magnetic moment which is also known as Bohr magnetism. Uh, so yeah, so then from here, like what happens? The total energy of your fermions uh, can now be so total energy of fermions epsilon is now your kinetic part and the part due to the uh, magnetic moment. So if you remember, if you place a magnetic moment in external external magnetic field. So you have a magnetic potential energy, which is the dot product of the magnetic moment and the magnetic field intensity, which you have also seen it like well before. So in your classical electrodynamics. So from there we can write it as the total energy will always have the kinetic part because even when we were considering fermions and bosons, these systems which we were telling that they have some certain energy, but they were not in any external magnetic field. So in that case, they only had kinetic energy. So it is this term, so which will always remain, and so do it will remain in this case. But now you have one more additional energy term that will be due to the magnetic moment, which will be given as magnetic moment with magnetic field intensity. So mu bs. So consider the magnetic field intensity is in like let's say z direction. So your magnetic field, and so it will be depending upon the magnetic moment whether it is aligned with the magnetic field intensity or opposite aligned, it will be either plus or minus. So since magnetic moment of this fermions can be either plus or minus mu b for spin half type fermions. So likewise, their energies are also p square over 2m plus mu bh, or it is there is a relative difference between them. It would be minus mu bh otherwise. So this is also if you see the, there is a shift in this energy between one state of the fermion to the other state. So this shift is known as Zeeman. Uh, uh, so this energy shift is due to Zeeman splitting. So Zeeman splitting is this when you put um, the fermions in an external magnetic field. So its energy is splitted into. So earlier, one fermionic particle used to have one corresponding energy, but now, depending upon its two spin states, its energy can split into two. Uh, yeah. So now, due to this, like you will find that um, like at 0 Kelvin, due to these energies, like you will find they will have certain Fermi energy at 0 Kelvin, and they will contribute to overall some magnetization. So uh, yeah, so magnetization again something if you find if you remember it is defined as something total net magnetic moment over the net volume. So So this magnetization, you find like as soon as you put fermions into some external magnetic field, like they that fermionic system, entire fermionic system attains some kind of magnetic property, which is which you can quantify it through by magnetizing. So yeah, so we can see a problem here, and uh, let me see a problem on it. Okay, so an ideal gas of n spin fermions confined to a volume V. So calculate the uh, zero temperature limit of uh, the chemical potential, then the average energy per particle, also the pressure and the Pauli spin susceptibility. Uh, okay, so um, So as I was telling that your energy of your fermions can now be um, uh, p square over 2m mu b over h. So basically, without magnetic field, your energy of fermions is just p square over 2m. But in presence of magnetic field, it becomes p square over 2m, either plus mu bh or negative of mu bh. So uh, so at 0 Kelvin, so if you remember, uh, the particles occupy all the energy levels below below the Fermi energy mu zero, and you yeah. So and your mu zero is the chemical potential that which you also see, like it is equals to Fermi energy at 0 Kelvin. So uh, uh, so now here what happens? Like the kinetic energy of the mm, kinetic energy of negative spin becomes this, that I'm denoting the particles having momentum negative p minus p square over 2m as mu 0 plus mu bh, and similarly for positive momentum spins it becomes mu 0 minus mu bh. So now to get the number of uh, so the number of negative spins will have uh, n minus. So you know the number density is something given as n over v, uh, something uh, uh, I think it is p minus q over hq. So this is something your number density is related is. So uh, let me just verify this. If you have any confusion, any doubt, you can ask. Okay. Yeah. So this is what it is. It is given this way. Yeah. Uh, so then basically your number density, your volume, you can take it to be. Um, so this is something given as. So like if you remember the density of states, the calculation that we have done. So from there you can uh, like you can easily find out that n by v or something was related to as 4 pi p cube, 4 by 3 p cube. You're basically we were like taking the phase space volume. So this is uh, n is your total number of uh, uh, fermions which uh, like uh, which like has the momentum p minus uh, in the phase space of the uh, uh, I mean uh, your n minus is the total number of fermions which is for the uh, fermions having p minus momentum and within the volume within the phase space volume enclosed by the p minus being the radius. So it was like something 4 pi uh, 4 pi p minus q. So it's like the volume of the momentum part of the phase space, and also you will have uh, the coordinate volume coordinate volume, and then divided by this normalization of this space volume h2. So this is something which we have done like many times before. The same thing, the same idea you can put here. So that will be your n minus. In the same way, you can write n plus, which will be 4 pi p plus q v over 3h cube. So then you have yeah, then your total number of particles, total number of, because I have written only for p plus and p minus, then total number of particles will be their sum. Total number of fermions will be n equals to n plus n minus. So this will give you 4 pi v 2m over 3 over by 2 3h2. Uh, so so I'm using this p plus p minus momentum from this relations. So that will give you mu 0 minus mu b h. You have to, since there is a square root, you can so square root can give you like two values, but you have to consider only the positive one because you are looking for the total number of fermions, so it has to be positive. So it would be the magnitude 3 by 2 plus mu 0 plus mu b h 3 by 2. Right. Uh, so from uh, let me check this. Okay, yeah. So now, like if you put h equals to 0, so with h equals to 0, you obtain the chemical potential to be. mm, So this is same as the like Fermi energy that you get for the fermionic distribution. So this is uh, this is Fermi energy at 0 Kelvin when fermions are distributed with no magnetic field. But with magnetic field, so you have this relation. So you have this. I mean, you can solve this equation maybe some numerical way to get exactly the chemical potential in presence of the magnetic field. So yeah. So then next we were supposed to. So if anything not understood, please let me know. Okay. So then the next one's on average energy per particle. So for spin plus half fermions, you have uh, p plus equals to the momentum value can be given as something this. Again, we are all like keeping ourselves at 0 Kelvin temperature, so T equals to 0. So this will be your T plus, and similarly for spin minus half furnace, you have P minus equals to 2m, and again your Fermi energy U0, UP, H. So all these places you can also write it to be epsilon S, being the Fermi energy. So yeah. So the average energy per particle, then first we can calculate what will be the total energy, because we know the P minus and P plus momentum. So again, if you remember the usual way, like how we calculate, we'll take the density of states and uh, do the calculation. Uh, so again, we can remember epsilon plus, let's say, the total energy for the corresponding to P plus uh, momentum. So in that case, if you remember, we were using yeah. So you can start with density of states. So you basically have to integrate out energy with uh, dxi dxj. So where ij both going from 1 to 3. So this will be uh, pxa or pj. So xi basically means xyz and pj basically means px py pz, or in uh, angular coordinates it would be r theta phi. So in that case I will also have a yeah. So that will, yeah, that is fine. So and also I will have a 1 over h cube normalized. So this is how we take energies and all calculate them. So in the same way we'll do. Uh, so first, if I take the volume part outside and also the surface part of the momentum, if I take the phase space surface defined by let's say p plus momentum, then I will have 4 pi p over h cube and 0 to p plus p square over 2m plus mu b h p square dp. So yeah, so only I have to integrate out this radial part. So so basically, since you can write your d cube t, which is dpx, dpy, dpz, or in angular coordinates, it would be p square sine theta dp. Uh, so dp theta, dp phi, and dp. So well, dp theta, dp phi, if you integrate out, and there will be dp. So if you integrate out dp theta, dp phi, it will be 4 pi. So you basically have d cube p as or uh, yeah. So if you integrate the theta part and the phi part, then you basically have phi and theta. Then you have so you will have only dp here. So that will be uh, p square 4 pi p square dp 4 pi p square dp. So yeah, so that is what we do. We are doing here the same thing. So yeah, like this is what, if you remember, like the usual process, like in calculating all these energies, average energies, or also momentum, or yeah, like whatever we have seen so far, the total number, average number. So it all goes by this same idea of phase space volume. So which we have also seen before also in yeah. Then yeah, so now you just have to integrate with respect to momentum variable, which is not so difficult here. So p square that is p4. So if you integrate out, it will be p5 over 10n. It would be plus your momentum goes from 0 to p plus, because your the momentum cell in the phase space, like it is extended from 0 to p plus, because you are calculating only for the energies corresponding to p plus momentum for the positive spin particles. Then ubh3 p plus p. Yeah, so likewise you will also have energy p minus, which will be 4 pi v over h cube p minus q. It will be p minus 5 again over 10n minus mu b h 3 p minus q. Then again you have the total number, and also you can get the total energy. So your total energy is E plus E minus. So average energy is E over N. So that is E plus E minus over N. So otherwise you can write it as 4 pi V over H cube N, then 1 over 10 M E plus to the power 5 plus P minus to the power 5 plus mu B H over 3 P plus cube minus P minus cube. Yeah. So if you take the so if your external field is very small, uh, the magnetic energy will be very less. So in comparison to the Fermi energy, so in that case you can use this limit mu bh is being very small compared to Fermi energy. Then you will have uh, E over N. You can just simplify out as mu 0 um, 1 minus 5 by 2 mu bh or mu naught square. Okay, but yeah, but your actual value of your average energy is this. Okay, so then we yeah, then we had to calculate uh, pressure. So pressure, if you know the approach, like the starting point is again like you take the derivative of your energy. So once you have the energy, you take the derivative with respect to volume at constant temperature, then that will give you the pressure. So the same thing like how we have done again last time around for the black body or the harmonic system that we have seen on the bosonic system. The same way you also apply here. That will be the same approach, but you are supposed to get some slightly different result every time. So that's what you like. I mean, you normally do in statistical mechanics. So this like all this recipe is very simple, but you have to just use them like very wisely, like at which places which you like what you need exactly, and you can apply that, and you can get the results. So pressure to calculate pressure again. So you can take the so you can do this. So now, but if you see your energy is given in terms of mu zero. So let's say you uh, So uh, let me check the energy which I calculated. Uh, yeah, okay, yeah, that is fine. So, like the pressure, you can calculate using the same definition as we've seen before. So, so like this one, you can check it. Like this, you will get it to be. Uh, let me. um, So this will be 2/5 n by v mu zero. Otherwise, this is 2/5 n mu zero. So mu zero is your Fermi energy. Then we also had one more question over here. So the Pauli spin susceptibility. So before calculating susceptibility, you need to know what is magnetization. So you first calculate magnetization. So magnetization again, like magnetization, as I was telling, so the net magnetic moment per volume. So you have uh, like you have for spin uh, plus half, you have uh, like its corresponding magnetic moment was plus mu b. For the minus, it is minus mu b. So therefore, you will have something. Uh, the let's say mu, mu b, and you have n uh, fermions or n plus fermions, which has mu b magnetic moment, and then you have uh, n minus fermions, which is negative minus mu b negative moment, and that is taken some over the volume v, so divided by v. So that is your magnetic moment. uh, uh, yeah, that is your magnetization m, and this is actually related as chi h. So again, from your electrodynamics, you remember this will be your some proportionality constant, but it is proportional to h. So this proportionality constant was your susceptibility. So this is your Pauli susceptibility. So in this case, since we are dealing with this formula, it would be Pauli susceptibility. So if you do this, like you will get around 3 times n mu b square over 2 mu 0 v. So so this you will get if you consider so if you by considering uh, mu 0 much greater than mu bh. Yeah, right. So then you have um, so yeah. So these are like what you can uh, yeah, like these are what you would have in case which you are talking about some fermionic system placed in a external magnetic field, but everything we have kept at zero temperature. Now, like what would happen if we take it to some like some finite temperature? So in that situation, let's say so you can consider the similar system. So um, an ideal case of n spin half uh, electrons, let's say, is placed at a weak magnetic field H. Then, like first, you uh, show that at high temperature, that is T much greater than TF, Fermi temperature, the system behaves like a classical Curie paramagnet and derive the magnetic susceptibility. So, so again at height at some so now we are at finite temperature. So so again the energies that you have is uh, uh, plus mu b h uh, and minus mu b h and corresponding to these energies. So suppose if we only consider this energy, we are not talking about any energy from the thermal motion. Then in that case, like you can just simply write down in terms of these energies. So so you have you can write down the one electron partition function. So that is z. You can so your partition function can be given as beta. So let's say your this is your epsilon one, epsilon two, epsilon one, and beta minus beta or yeah beta epsilon 2. So only for two energy levels. So this will be simply exponential beta mu b h then plus exponential minus beta mu b h. So this is just cos hyperbolic beta mu b h. So now you can write down your average magnetic moment per electron. So so uh, the so to get the susceptibility, like just as we did before, we need to first know the magnetization to get the susceptibility. So for susceptibility, you have to first do magnetization, and for magnetization, we need the total sum of magnetic moment, or uh, or at least the average magnetic moment. Uh, so here what we can write, uh, average magnetic moment per electron. So this average magnetic moment, you can write it as your 1 over your partition function z1 mu b exponential of beta mu b h minus mu b exponential of beta minus mu b h. So and this time, like if you simplify this, like since your c1 is cos hyperbolic, and on the numerator you have something of the type of sine hyperbolic. So you will have something mu b sine hyperbolic beta mu b h over cos hyperbolic beta mu b h. So that is mu b 10 yeah, 10 hyperbolic beta mu b h. And now to get the susceptibility, finally you can calculate the magnetization, which is your total magnetic moment. That will be n times. So n is your total number of electrons. So magnetic moment per electron is you what you found, which is mu b 10 hyperbolic beta mu b h, and you divide it by the volume. So yeah, again, to solve this, like we'll use the weak field approximation, like as we did just before. So that is mu bh. Uh, so this mu bh less than. So that time we were using mu zero. So mu zero was your uh, Fermi energy, but here since we are at some finite temperature, so we can say for some when we are already at some finite temperature, we can write maybe the thermal energy or something with in terms of kBt. When so this is your weak field condition. So, so for so in that case you will find your magnetization will go something like 10. So this also means mu p beta mu ph is much less than 1. So in that case, your 10 hyperbolic, let's say x, will be same as x. So because x is very small, Then your magnetization could be written down as n times v mu b beta mu bh, or magnetization is n over v mu b square, and beta is kbt. Uh, so now whatever you uh, have it right here, so that will be your chi. But this will be not always true. I mean, the actual definition has to be something for susceptibility is del m over del h, because for some kind of material, like chi can also be uh, not linear, like the it could be not linear, like it could be not linear, like it could be not linear. Okay.
Okay.
uh,
Uh,
like I
like
had
I had a bit
sound
sound problem here.
uh,
Uh,
let
Let
me
me see.
uh,
Uh,
okay, so I'm having
okay, so I'm having a bit like
sound issue over here.
sound issue over here.
Sorry for that.
Like sorry for that.
Trying to fix it.
I'm trying to fix it.
Uh,
Let's see. Let's
go with this
go with
for a
this
moment.
for a moment here.
So yeah,
So yeah.
so I was
So
telling
I was telling the
right way to
right way to
calculate
calculate your
susceptibility.
susceptibility.
So once you
So
have
once you have your
magnetized,
magnetization,
you can
you can
take the
take the
derivative
derivative
uh,
uh,
with respect
with
to
respect to magnetic field intensity, which is your
um,
uh,
yeah.
yeah susceptibility.
So then,
So then
so here also,
here also,
if you
if you do,
you will
you
find
will find out
out
uh,
your chi
your chi
will be
will be
uh,
uh,
n over
n over v
uh,
uh,
mu b
mu b square
kvt,
kVt.
that is,
That is,
so you
so you
find
find
q is
Q is
proportional,
proportional to
uh,
uh,
yeah, chi is
chi is
proportional to
proportional to
1 by
1
t.
by t.
So this
So
is
this is your
uh,
uh,
Curie's law.
Curie's law.
So
So
this is
this is
how
how
at finite
at finite
temperature
temperature
your
your
susceptibility.
susceptibility varies.
So
So
earlier
earlier,
we
as
saw
we saw,
at the
at
zero
the zero
temperature,
temperature,
uh, in the one
the one
I
which I
showed you
showed
right.
you right here.
So
So
so again,
so again,
you
you
will
will
find this
find this
susceptibility in
susceptibility
the
in
weak
the
field.
weak field.
So
So
uh,
um,
here you
here
find
you
it
find it is
basically a
basically a
constant.
constant.
I mean,
I mean,
constant in the
constant in
sense
the sense it is not
depending on
depending on
temperature, right?
temperature right here.
But
But
here you
here you
see
see the
inverse
inverse
temperature.
temperature relation.
Uh,
Uh,
yeah,
yeah,
let me
let
check
me
this
check the
out.
sound.
Okay.
Okay.
But like hopefully this time there is no such echo issue. Yeah. So yeah. So at finite temperature, like you can show how your susceptibility like depends on inverse temperature, which is your like well-known Curie's law, and at the 0 Kelvin, which we found it to be something not dependent on temperature. So yeah. Then so here you can now you can uh, look this final bit here. So so comparing mm, the obtained result, the obtained result, uh, or let me see the question here. Okay, like comparing the obtained result with the following Curie law. So that is chi n over v mu square effective over 3 kVt. So in this you determine the effective uh, number of Bohr magnetons per electron. So Bohr magneton, like so far what we've been writing mu b, that is your basically the Bohr magneton, the magnetic moment that you get one, like that is basically the magnetic moment of the ground state of the hydrogen atom. So basically when an electron goes around its nucleus, that is the Bohr magneton. So we take it as units in general in quantum mechanics to measure quantities, especially like magnetic moment. So here we need to calculate what would be the number of Bohr magnetons when from this susceptibility that we have it right here. So this is some effective uh, value. It is given from the Curie's law. So again, uh, let's say uh, so the relation which we got previously is this n mu b square over b cavity. So n over b, yeah. So now if you compare both the forms, you will find mu b square equals to mu square effective. So basically, this Q, the sky, which is given in Curie's law, it is written down in terms of effective magnetic moment. So in that case, like your effective magnetic moment, like is basically given as mu effective square is 3 mu b square, or mu effective is basically root 3 mu b. So so that means this many amount of effective uh, Bohr magnetons you will have. Uh, other or one more thing which I was trying to like uh, talk about here, this mu effective, like let's say from this uh, you like from this find out the spin of particles. So I have already said electrons here, but doesn't matter. But here, from here, what you can do here. So this overall factor which you are getting. This is like in uh, this is something effective moment defined from the Curie's law. So from Curie's law, you can write from that is something mu b g times square root of uh, s times s plus 1. So this is mu effective times mu b. So and this g is your Lent g factor. So which is like here it is given to be where g is given to be 2. So, so in that case, so you can find out. So if your mu effective is root 3 and z and 2 s times s plus 1 mu b, so or you basically, yeah, so you find that s is half. So I've already said it uh, at the question itself. So we are doing it for electrons, but nonetheless, so this is how the effective uh, magnetic moment of Curie's law is expressed. So yeah, so that is what we have here. Like if there is anything, any other problem or issue, we can. Uh, yeah, if there's any question or anything, like we are almost done for today. So uh, so we will not have any more questions here. So we are already out of time. Questions here. So we are already out of time. Questions here. So we are already out of time. Okay. So I'm also having issues with this noises around here. Like I'm having some trouble in controlling this echo in my devices. So yeah. So if there is no other like thing to ask or anything, any other problem, then probably we can discuss again for the week 6. Uh, like yeah. So we'll see again next time. So yeah, so that's it for this session. Yeah. Yeah. Thanks.